We're recording. Okay. Next lesson. Huh?
We should be studying this lecture on 30th of September.
Oh, that's just when I made the file. Please. Did you write the title down, Grace? No, you didn't. Oh my goodness, that's what it says. Yes, rocket science. It's not. It's actually not so difficult. Right, can we go on now? So, another way to state Newton's second law is as follows. Force is the change in momentum over the change in time. And you might be thinking, what the heck is that P? Well, that's new. Delta P is the change in momentum. And I thought I put the definition in this formula here. I'll write it in here. What exactly is momentum first? I don't think I told you momentum. Momentum is mass multiplied velocity. This is called momentum. So then delta P is the change in momentum. And delta T is just how much time has passed. P is a new thing called momentum. And momentum is mass multiplied velocity. So Amanda, if the mass is big and the velocity is big, then the momentum is very big. If the mass is small and the velocity is very big, then the momentum could be big. And likewise, if the mass is big and the velocity is small, then the momentum could still be big. So let me give you examples. A truck. A truck has large momentum because its mass is big. A bullet has large momentum because its velocity is big. A racing car, a sports car, has a lot of momentum because its velocity is big and the mass is big. A physics teacher has small momentum because he is not fast and the mass is not too big. Yeah. So momentum is just mass multiplied velocity. Okay. Right. Can I continue here? So Newton says also that the force is the same as the change in momentum over the change in time. And let me draw a little picture here. Let's say this is M with U, and then it increases to V. You understand my picture? Like a little car here. Little car. Alright. Amanda, what's the momentum here? What's the formula for momentum here? It'll be M multiplied V. Yeah, that's it. And Grace, what's the momentum here? U. Yeah. So the change in momentum is mv minus mu. And the time is just the time. Now, does anybody recognize what this is? V minus u over t. It's A. Because remember, you have V equals u plus AT. So V minus u over over t equals A. Does that look familiar?
Yeah.
Yeah. So this is just saying that you could say F equals MA, or F equals change in momentum over change in time. So it's just two ways to say the same formula.
Okay.
Huh?
So just common M,
Yeah.
but there is no M in T.
Doesn't matter, it just needs to be in the top.
So then it means like equals.
Yeah, that's the next thing. That's the next thing. Can I go on? Yep. So why do we bother with this new formula if F equals MA works? Well, the reason is it works very well when the force is being applied for a small time. And anyway, the other reason we use it is it works very well for rockets. But look, the reason is not important right now. You'll see the reason why with some examples. I just need to give you some new vocabulary. Impulse is the change in momentum. That is, we call this delta Pi, the impulse. So just the definition, please, just the definition. Okay. Oh, thank you. Okay. Let's have a look at our example. So a 1,200 kilogram car crashes into a wall at 20 meters per second and is brought to rest. What's the impulse? So let me just draw the story for you. Car, 1,200, 20 meters per second. Everybody's happy. Driver looks at his phone, sends a text message, and then the next thing you know is, bam, no more driver. Now this is 0 meters per second, but it's still 1,200 kilograms. So my question is, what is the impulse? Well, what's the formula for impulse? Now what's the formula?
P.
Not quite P. The change in P. Huh? Delta P, yeah. So what's the momentum at the end? MV. And what's the momentum at the start? MU. What's the mass at the end? 1,200. And the velocity? 0. At the end? Minus 1,200 times 20, which will be 24000. Now I didn't say what the units are, but I hope you can see what the units are. What's the units for I? Well, what's the units for delta P? Well, what's the units for MV? So what's the units for MV? MV? What are the units? Come on, don't be shy. What's the units for MV?
That's not 2,400. That's 2,200. And it's minus.
Wait, it's not 20, or minus. It's not 24?
No, it's 22,800.
No, it's 24. With a minus, yeah. Sorry, who was telling me the units? What are they? What are they? Units! People, give me the units. No, you cannot have forgotten everything you learned in the first lesson already. What are the units here? Kilogram meters per second. Kilogram meters per second. 1200 minus 1220, the same answer. Okay, did you write this down? You got this? So tell me this, is impulse a good or a bad thing? What do you think? Impulse is bad. What I mean by that is, if there's a lot of impulse, it means there was a lot of force or a lot of change in velocity. So because this is really big and really negative, it means there was lots of force. Impulse is like pain. Okay? The bigger the impulse, the more pain was felt. Yeah. The next example. A hammer hits a nail with a force of 100 newtons and the nail moves with velocity of 2 meters per second. How long was the force applied to the nail by the hammer? Okay, so I'll draw it for you so you can draw the picture. So what you have is you have a nail and then you have a hammer. Yeah. I can draw that better, I know I can. No. Nail. It's a hammer. Deal with it. And the hammer gives a force of 100 newtons, and then the nail moves at 2 meters per second when you strike it.
And what did you have to find?
I don't think I gave you the mass of the nail, which I'll give it to you if you need it. The question is, how long did the hammer hit the nail for? Because, you know, when the hammer hits the nail, it just hits it for a small time, you know, like less than 1 second. So my question is, how long was the time when the hammer was touching the nail? The contact? How long? Okay. So, the impulse. Actually, I should give you the mass of the nail as well. What would we say? Maybe 0.01 kilograms is the mass of the nail. Okay. Impulse of the nail. That is the change in the momentum, which would be mv minus mu, which would be 0.01 times 2 minus 0.01. And what's the U for the nail? 0. Kilogram meters per second. So the impulse is not too big for the nail. Okay? But this is not finished. How do I get the time? Well, I can use Newton's second law. Newton's second law, F equals impulse over time. That means that the time equals impulse over F, which here would be 0.02 over what? 100. Which would be 0.0002, which maybe is a little bit too small, 0.2 milliseconds. So, this is what I was talking about earlier in the class. The reason this formula is useful, we really like this formula because it can give us this time, especially when the time is really small. This is the way we usually use this formula. Okay? Next example. I don't think I'll do this one because it's just like the last one, so I think you have the idea. The only difference here is a football player kicks a football, but it's the same as the hammer hitting the nail. What I really want to do is this one, which is in the exam. So another big advantage to using this formula is that you can use it to calculate the force provided by rockets. That's right, rockets. So we need to have a think about the gas that's coming out of the back. So let me draw this for you, rather than all this text. Huh? What stop dissing my rocket. Right. So if we think about a rocket, hang on, don't confuse me. It's a rocket, okay? What's inside the rocket? There's some gas inside the rocket, and then the gas is burnt, and the gas comes out of the back. Yeah. Now, what is the momentum of the gas here? The mu of the gas will be 0. Why? Because the u is 0. But then here, what's the momentum? It won't be 0, it'll be mv. So what is the impulse? It is the change in momentum, which will be mv minus mu. But the mu is 0, so the impulse will be mv. But Newton's second law says F equals delta P over delta T. So that is mv over T. Now that's how much force is firing the gas downwards. But you remember my example with the balloon? So the air comes out of the back, that's the action. What happens to the balloon? It goes forward. Will this force equal that force? Yes. It's equal and it's opposite. So that means the force up here is also F. So this gives us our formula for the rocket. The force going up is equal to, now what I'm going to write here is delta M, and what I mean by that is how much gas comes out per delta T. And then V here is the speed of the gas divided by delta T, which is the time. And we normally do this per second, normally. So normally that means that the delta T is 1, because we do it per second.
Changing the mass.
I'm just writing delta M just to make it clear that it's how much mass comes out per second. It's not the total mass of the gas, because most of the gas stays inside and only a little bit comes out per second. Okay? No. Not okay. Okay. Ready now? Let me just make some. Okay. Next example. Let's look at an example of this now. Right. So again, don't worry. Lots of English, I know, so let me just draw what you have here. You have a rocket of 4,570 kilograms. 4,570 kilograms. And what else do I say? The gas comes out with a speed of 4462 meters per second. So this gas is coming out at 4462 meters per second. And I also said each second 7,485 kilograms of gas comes out. So that is each second. The mass that comes out is, I forgot already, 7,485. 7,485 kilograms. And that's each second. So we're looking at per second, which is the normal situation anyways. So, there is an up force here, and we have a way of calculating it. It's delta M V delta T, but the delta T is 1, the delta M is here, and then the velocity is here. So if I just multiply these two numbers together, 7,485 times 4,462, I get a very big number. I'll get 33.4 mega newtons. How big is mega? 10 power 6.
Okay, T is 1 second.
Yeah, we're doing this per second.
So we want to do the second again?
Oh, you could, yeah. No, but we, in the exam and in class, we often look at the initial force. But you're right, then you could do the next second, and so on.
And you divide by 10,485.
Divided by what?
No, that would be divided by 2.
The time is 1 second. Oh no, it would still be 1 because the delta T is how much time has passed since the previous moment. So if you do it in 1 second pieces, the delta T is always 1.
Can you do the calculations?
Perhaps. 7,485 minus 4,462. It is correct.
No, nothing. No.
I just multiplied two numbers. 7,485 multiplied 4,462. Yeah? I'm using this formula. M multiplied V divided by T. Now, can I scroll down a bit? No, actually, I'll just draw it here. So we have this force going up, but there's also a force going down. What's this force going down? The weight. So let's calculate the weight. That's equal to mg, which will equal 4570 times 9.81. Which will be 44832 newtons. Grace, what's the total force? You can tell me how to do it. Yeah, it's MA. But I want to know what the F is. Like in the example I showed you with the weighing scales. Anybody? Amanda? What's the F here?
W minus...
No, the other way. Not W minus, the other one. This one minus this one. So it will be 33.4 times 10 to the 6 minus 44,832. And yes, Grace, like you said, this should equal MA. So this will become 33.3 times 10 to the 6 equals 4570A.
3.4.
Oh no, but I did the minus. So roughly 33.3.
Force is reaction force minus weight.
Yep.
2.9, okay.
So you have this huge acceleration at the start, which, you know, means rockets move fast. Yep. So really there's only one new formula, maybe two new formulas for today. F equals impulse over time. And what is impulse? Change in momentum, which is mv minus mu. Yeah. Yeah. So let's see, you should have, this is the impulse, and then Newton's second law can be written like this as well. So there's two formulas now for today. Okay. Time for questions. I think I don't have any more examples, do I? Oh yes, okay. I do have one more which I'll finish on. Right, I'll just draw it for you. Yes? No. That was the draw, wasn't it?
Yeah.
Question? I'll be finished in a moment. Do you have business in here? Yeah. I'm going to pretend I'm not... Oh, hang on, sorry. Let me just pause the video for a second. I'm sure it will be fine. No, there's not. Okay, last example and then we'll finish. Still cold. Okay. Right. 12, there's a wind blowing at 12 meters per second. So you have this wind blowing at 12 meters per second, and it hits a student. That's a student now. And the student is 1.6 meters tall, and also he is 40 centimeters wide. Okay, and the density for air is 1 gram per centimeter cubed. So my question is, how much force does the physics student feel from the wind? Do you understand what's happening? Here, it doesn't look like it, but this is actually a physics student. Okay, so my question is, how much force does he feel from the wind? That's the question. Right, let's have a look at it. So I should use the formula F equals delta P over delta T. So he feels the wind blowing him. So that would be mv minus mu over, and we'll do the time, we'll do it per second as well. Should we go?
You can check if it's...
Let's go.
Alright. Wait. We have maths later today, don't we? Wait, hang on, wait. Let me think, can I do this quickly enough? Yeah, I'll finish it really quickly. Don't worry, I won't let anyone die. Okay, so the air is at rest, but then it gets the wind blown on it. So the U is 0, and the M is 12. The V is 12. We don't know the M. Yeah, we don't know the M, but we know the V is 12. Okay.
And U is 0?
And the U is 0. When you think about it, like the air is like at rest, and then the wind blows him. So the U is 0, and then the wind blows, and now it's not 0. Does that make sense? Okay. Now the problem is we don't know the M, but what we do have is the density. Does anyone remember the density? Density is M over V.
Yeah.
So now we have F equals 12 density V. Now the problem is it's in centimeters cubed, so we'll have to convert it to kilograms. So let me see, how big is centi? It's 10 to the minus 2, and it's centimeters cubed. And then the mass multiplied by it. Wait. Please don't, you're panicking me. I want to finish it. Okay, so that will be that many grams. Okay, so if I calculate this, that is the same as density is 1,000 kilograms per meter cubed, I think. I sure hope so. You know what, I think I made this too big. I'm going to change it to 0.1 gram. 0.1 gram. So that means that the density will be 100 kilograms per meter cubed. Even that I think is too big. We'll say it's a heavy wind, I don't know. Okay, so this here would be 12 times 100 times V. So that's 1200 V. Now the problem is I don't know the volume. And then if I knew the volume, I'm finished. So does anybody know what the volume would be? Well, if you look here. Here's the physics student, and the wind is blowing 12 meters per second. So in 1 second, how far does the wind travel? 12 meters. So the volume of wind is like this big rectangle. That's the volume of wind. It's like a big box. So the volume is actually 12 times 1.6 times 0.4. You think about it like a big box of wind in 1 second. It's 12 meters long, and this pushes it. Yeah, does that make sense?
Yeah.
Okay.
So I'll do that times that times that times that. So I think my answer is not realistic. 9,000 newtons, which would like kill him. I think I made my density too big for wind. Look, the reason I wanted to do this one was because there's an example like this in the homework, okay? Where there's a wind blowing a student and you need to work out how much force is hitting him.
Yeah.
I know, I'm sorry, I did it very quick, but is there any questions with this? And look, I'm going to do another example next time because, like I said, there's one in the homework as well. Hold on. Well, alright, hang on.